So counting, 4-6. Counting is referring to permutations and combinations. Alright, they're very similar. Their formulas that we eventually will get to in a second are just a little different. But there's one main difference between the two. So let's see. Permutation of items are arrangements in which different sequences of the same item are counted separately. For example, with the letters A, B, and C. Here are the different arrangements. ABC, ACB, BAC, BCA, CAB, CBA. All of those combinations they are listed would be counted as 6 different permutations. So to break this down into something a little more concrete, let's say that I was selecting 2 people in this classroom to go on a special trip to Mars. And let's say that I randomly selected 2 and I got Mr. Funk and Miss Ray on one of my selections. Okay, well, let's say that I made another selection. I put them back, and it just so happened randomly I chose Miss Ray and Mr. Funk. So those 2 groups, if we think at it as a permutation, would be counted as different groups. But really, are they different groups? Well, no, they're not. So that would be an example of when we would want to call it a combination, not a permutation. Look at the definition of a combination. Combinations of items are rearrangements in which different sequences of the same item are not counted separately. For example, all these groups here they list that have the same letters, all those would be considered to be the same combination. Just like if I chose 2 people and then I chose two people again and I got those same 2 individuals, I just chose them in a different order, it'd be the same group. Okay, that's a combination when order doesn't count. Alright, so that's the difference. The main key to understand the difference between a permutation and a combination is that with a permutation, different groups will count separately. Alright, with combinations, different groups of the same 3 items, 2 items, ever how many items, will all considered to be the same combination. Alright. Here's a mnemonic that your book points out. When trying to remember which of the 2 preceding terms involves order, think of permutations, position. Permutations, position. Permutations, position. Where the alliteration reminds us that with permutations, the positions of the item makes a difference. You might also consider, let's see, the alliteration combinations committee. Combinations committee. Where those words remind us that with members of a committee, rearrangements of the same members result in the same committee. So the order does not count. Okay. Alright. So to be able to work out combinations and permutations, of course we have formulas, but, and you can look here, at least in this edition of the book, these squares right here, they should all be multiplication signs. So if there's a newer version of the book, then it will actually have the x's there, but this electronic version, the x's are not there. So, and this is explaining what is factorial. What does it mean? Factorial is a way to express this operation. Say I had 4 factorial. The way that we represent factorial is an exclamation mark. So yes, we stole that from English, right? It's not that it's 4, it's that it's 4 factorial. What that means is 4 times 3 times 2 times 1. Okay? Counting down and multiplying all the numbers until you get to 1. So 4 factorial is 4 times 3 is 12 times 2 is 24 times 1 is 24. Okay? Look at 5 factorial. It's 5 times 4 times 3 times 2 times 1. So 5 factorial would just be 5 times 4 factorial, right? And that would be 120. You can see factorial goes up really fast. 6 factorial, of course you know it's 6 times 5 times 4 times 3 times 2 times 1. That's 720. So they go up really, really, really fast. So depending on the type of calculator that you have, you know, I don't know how, depending on the type of calculator you have, there's no telling how many places that your calculator will go. So like if you try to do 12 factorial, like on this calculator, yeah, it works. But 25 factorial, I mean, look how big that number is. I don't even know I have no idea how big that would be. But I guarantee you most calculators won't carry it out that many places. Some of these formulas require us to divide things like 25 factorial, say, by 20 factorial. That's just the way that the formulas sometimes work out. But we don't expect you to have a calculator that would take out 25 factorial. So one way that you can simplify factorial, if you have a formula where you get factorial in a numerator and denominator, let's say I had 25 factorial divided by 20 factorial, you can't just simply simplify the fraction. That doesn't work. What you have to do is you write out the numerator. It's 25 times 24 times 23 times 22 times 21 times 20 factorial, and you stop there because that is the same number that's in the denominator. 20 factorial is down here. And so since you're multiplying up top, that will cancel that out. So 25 factorial divided by 20 factorial, if you were to do that in a calculator, sometimes you might not get the right answer because if a calculator can't hold but so many places, then you're not going to be able to get the right answer. So if you write it down though, and you simplify it, now we can go to the calculator and we can say 25 times 24 times 23 times 22 times 21 and get our answer. Still a big number, 6,375,600. It's about what I make a year, by the way. I mean, it's still a big number, but it's a manageable number. Okay. So the formulas that we're going to use, or that you use for permutations and combinations, are listed on page 196. Let's first look at the formula for permutations when all of the items are different. That would mean, you know, each item that you're selecting, that you could possibly select, is different. And here's the notation. And permutations can be written, and this looks a little strange, especially if you've never seen it, but a permutation can be written like this: 3p, say 1. Okay? If you don't know what that means, then I guess as long as you had the formula it wouldn't matter, but you need to know what that actually means. Okay? And so let's look at the formula. NPR. That means n factorial over n minus r, so the first number here minus the second number, factorial. Alright, so the n is the different items that are available. The r is how many of those items we're selecting without replacement. Again, the n is the number of items that we're choosing from, or that are available. The r is the actual number that we're choosing. So n factorial over n minus r factorial. So if I wanted to work out this permutation, this would be 3 factorial divided by 3 minus 1 factorial. So that's 3 factorial divided by 2 factorial. Or, now one real easy like this, you could just work out the top and work out the bottom. Or you could use your simplification skills that you just learned. The simplification skills to pay the bills. Cancel out, you're left with just a 3. So that permutation is just a 3. You say, well, how would that even relate to a real world problem? Okay, if you think about this like those sets of letters, like we have A, B, and C. How many different ways can I choose one letter of those 3? Yes, that's a real easy real world application, but how many ways can I choose one? I can either choose A, B, or C. That's 1, 2, 3 ways. That's why I got 3 over here. Of course, we wouldn't have to use it on something like that that's so simple. Now, this second rule here is if some of the items are identical to others. So like you say, when would I ever come in contact with a situation like that? Well, what if you had a bag of marbles and say 5 of the marbles were blue and 3 of the marbles were yellow and 6 of the marbles were red, and then we wanted to know the probability that if we selected you know, maybe a set of those, well, it's going to matter because some of the items are the same. So the permutation rule is n factorial divided by n sub 1 factorial times n sub 2 factorial, so and so forth and so on to n sub k factorial. So this right here would be like if you had 6 red marbles, it'd be 6 factorial. If you had 3 blue marbles, then it'd be times 3 factorial. If you had, I don't know, 10 green marbles, it'd be times 10 factorial. The top number would be the total number factorial of ever how many marbles there were. Okay. They give an example here. They did on the last one too. Maybe worth reading through. Have these 10 letters. You see how some of these are repeated? And we want to know if we have these 10 letters, then how many different permutations could we come up with? So there's 10 letters. The top number is 10 factorial. We have 4 A's. That's 4 factorial. 2 B's. That's 2 factorial. 2 C's. That's 2 factorial. Have a D. That's 1 factorial. And an E. That's 1 factorial. Well, of course, you don't put 1 factorial on the bottom because multiplying by 1 is does nothing. Now, because of the way that permutations and combinations work out and the way that factorial works out, if you ever get 0 factorial, it's defined as 1. So if any part of your formula you ever get a 0 factorial, it's not 0. That's equal to 1. We just have to do that to make factorials work out in formulas. Alright, so what if order doesn't count? If order doesn't count, it's a combination. Here's the formula for a combination. Alright, that should be NCR. This n needs to be up a little bit. N factorial divided by n minus 1 factorial, which is wrong, times r factorial. So it's not n minus 1, it's n minus r. So again, if you're using a printed version, it's probably in the right form, but here that should be an r. Make sure you don't write a 1. It's n factorial over n minus r factorial times r factorial. Now remember, a combination is when order does not count. So that means if you have different groups that have the same items, all those groups that have the same items are the same group. Alright, and so here's an example. If you have the 5 letters A, B, C, D, and E. Alright, and 3 of them are selected without replacement. that would be 5C3. It's 5 factorial divided by 5 minus 3 factorial, that's the n minus r factorial, times r factorial, or 3 factorial. Alright, so that's 2 times, because that gives you 2 factorial, times 3 factorial, or 2 times 6 in the denominator. That's 3. Because the problem says there are 5 letters, we're choosing 3 of them. Alright, so 5 factorial is 120, 2 factorial is 2, 3 factorial is 6, 120 divided by 12 is 10. So that means that you could get 10 different groups if you chose 3 of those letters without replacement. Alright. So again, remember the difference between a permutation and a combination. A permutation, if you get different orders of items, those are considered to be different groups. Alright. Combinations, if you get different orders of items, those are considered to be the same group. You say, well, how would you know in the real world? Are there such things as permutations and combinations? Of course there are. All this is applied statistics. So, all right, so let's look at problem number 8 here. Harry Potter books. There are 7 books in the Harry Potter series. If the books are read in a randomly selected order, what is the probability that they are read in the order that they are written? Okay, so this isn't a combination or permutation. This is just a problem that we can either use factorial, or we could use maybe like our common math sense to figure this one out. Now this is a probability. There's only going to be one way to read them in order, right? If you get any book out of order, then you haven't read them in order, okay? And we're saying we read them in a randomly selected order. So if we have 7 books, then when we select the first book, we have how many choices? 7 different choices. When we select the second book, we've already selected the first one, so that takes one away from the total. So then we'll have 6 choices, 5 choices, 4 choices, so on and so forth. Now this is a probability, and there's only one way of getting it right. Also notice that if I'm multiplying all these, this is the same thing as 7 factorial. So if I want the probability of reading those in the right order, then that's going to be 1 over 7 factorial. Okay, 7 factorial is I guess it's kind of a big number. You can either work it out or you can use your calculator, and you'll get 1 out of 5,040. So that's the chances you read the books in order if you randomly select the books. It's a probability. There's only one possible way that you can read the books in order. There's 5,040 possible ways to read the books in order. So if only one of those is correct, then it's 1 over 5,040. Okay. So let's see how that would differ from maybe a combination or a permutation problem. Let's see if we can find one. Alright, I believe this is one. Number 9 looks like a combination or permutation problem. Lady Antebellum songs is the topic. A fan of Lady Antebellum music plans to make a custom CD with 12 of her 27 songs. How many different combinations of 12 songs are possible? Is it practical to make a different CD for each possible combination? So we have 27 songs, and we're going to choose 12 of those songs. How many different combinations of 12 songs are possible? is it practical to make a different CD for each possible combination? So that there tells us combination. This is a combination problem. We didn't even have to figure that out. And recall the definitions for combination and permutation, right? And what the difference is. That's important. One, permutation, if you have, I guess compared to this problem here, would be if I picked out 12 songs and made a CD, and then I picked out 12 more songs and they happen to be the same songs but in a different order, with a permutation we would count that as a different CD. But with a combination, as long as we chose those same 12 songs, the order wouldn't matter. It would be the same CD, just in a different order. Okay? So if we weren't told this was a combination, we could figure it out that way, because different CDs with the same songs would still be considered to be the same CD. There'd be no use. You couldn't get anything else out of the CD than what's burned on it. So let's take that into account. Now, this is a combination. Let's see, this is problem number 9. It's a combination. We have 27 items and we're choosing 12. Okay. So our formula is n factorial over n minus r factorial times r factorial. Alright, so it's going to be 27 factorial divided by 27 minus 12 factorial times 12 factorial. Alright, 27 factorial is, if you punch that in the calculator, you're probably going to get something in scientific notation, because it's a very, very large number. So what I would suggest doing is first simplifying this by counting down from 27 until we get to, what is 27 minus 12? It's going to be 15. So I'd say the numerator was 27 times 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 times 17 times 16 times 15 factorial. That's over 15 factorial times 12 factorial. Alright, so now in your calculator, the smartest thing to do would be to say 27 times 26 all the way until you get to 15, or I'm sorry, 16. And your calculator still may try to put stuff in scientific notation. Just as long as you don't clear out the number, that should be okay. So you take that and you divide by 12 factorial. Alright, I did that, and I got 17,383,860. So that is the total number of different CDs that you could make. That problem then says, is it practical to make a different CD for each possible combination? Not really. I'm not going to make over 17 million CDs. Sorry. That would take a long time. Alright. Let's look at another problem. Let's look at problem number 12. Alright. With a short time remaining in the day, a FedEx driver has time to make deliveries at 3 locations among 8 locations remaining. How many different routes are possible? Okay, so he has 8 places that he can go. He's going to choose 3 of those places. Okay, so if we had down the 3 that he chose, let's say his truck is right here, and he went here, then here, then here. That would be a different route than if he went here, here, and here. It may be the same length, but it's still a different route or different route. So what that means is this is a permutation because the order doesn't matter. It's still a different route. Okay? So this will be 8p3 or n factorial over n minus r factorial. So that's 8 factorial over 8 minus 3 factorial. So that's 8 factorial over 5 factorial. And you can work this one out pretty quick by hand by just reducing the numerator down to 5 factorial and then canceling that out. Okay, the only thing else we have to do is 5 times 7 times 6. 5 times 7 is 56 times 6 is 336. So there are 336 unique routes that he can take. All right. Now we went over a formula with a permutation if we had numerous items of the same type. So if you look at problem number 14, problem number 14 is a permutation that you would have numerous items or different items of the same type. Problem number 14 says, how many different ways can the letters of statistics be arranged? So we need to look at the types of letters. It's not the actual letters that matter. I mean, they do matter, but they don't matter in a sense because they could be some other letter if we had the same number of each. So if you look here, you have 3 S's, you have 3 T's, you have 2 I's, you have 1 A, and you have 1 C. So the way we can find this answer, oh, and how many do we have total? We've got to count our total number. There's 10 total letters. So we have 10 total letters divided by, we said there were 3 S's, so 3 factorial, 3 T's, 3 factorial, 2 I's, 2 factorial, and then 1 A and 1 C, 1 factorial, 1 factorial. And so I need to work each one of these out and then multiply. All right. So 3 factorial is 6. So my denominator is 6 times 2 times 1 times 1. All right, 10 factorial is pretty big. So 10 and then I'm looking for factorial right there. The n with an exclamation point. So that's 3,628,800. All right, the bottom is 36 times 2, that's 72. So we need to take this number and divide by 72. So 50,400. So there are 50,400 ways to arrange the letters in statistics.